Yeah, welcome back to High Performance Computing. We have our lecture 4 on advanced MPI techniques and the second part of it. So the first part connected in a way really different lectures we had before, from domain decomposition in lecture 3 where we dived in, connecting it back to lecture 2 on MPI, the environment. And we learned different communicators which really nicely abstract from the underlying network level. So I could easily communicate with my neighboring ranks in order to maybe do a numerical weather prediction. And all I need to do is stay on the rank level, right? So I don't need to do about IP addresses. I don't need to know any about this. My MPI environment gives me all of that, basically, if I specify the right communicator. Furthermore, we also still learned that, of course, MPI has a broad set of application. And with this comes lots of requirements for different message exchanges. One of it was non-blocking, which could be helpful in many situations, especially if the load is not so equal. You will understand that non-blocking situations can occur often. On the other hand, non-blocking communication is often also the cause of performance issues, right? If you, let's say, program very wildly in this. And if you have a later, in your course, maybe a bigger application, you will see that a little bit. Some of you that take the final project, for instance, in the fishing or so. But in the end, we learned that, of course, even if I abstract from the network in part 1, right, we still have a real network underneath. So you learned the mesh, you learned the fat tree. We also learned that the fat tree communicating with each individual core with a fully connected network might be quite nice. But on the other hand, applications often show some regional behavior. I want to know my neighbors in a way, or a certain of regional forecast connecting to the global picture. So in a way, that's maybe not needed. So we oversubscribe certain connections based on switch hierarchies in this tree. So in order to make it cheaper, because today, by far, the network interconnectivity is the most expensive part. Computing is actually quite cheap. Not completely true, because NVIDIA has a shortage of GPUs to give, right? So that's a big problem we have these days. You have long waiting time to get NVIDIA GPUs, and if you have orders of thousands in HPC. Hence, this is becoming also more and more a cost factor, the accelerator. So you would have the interconnect, the accelerators, but CPUs by large, and the memory is basically something which is the most cheapest part of it. And hence, there's one thing that we didn't touch, and this is data, right? We talked about lots of computational complexity. What is now the point of using MPI with I/O, input, output, and we call that specifically parallel I/O because I have a parallel application. I want to do programming in parallel. Hence, let's go into this and shift the view again. So we shifted the view in the last part where we said, okay, computing intensive are our cores. Let's put an emphasis a little bit more on the connections that took us to the network. Now we do one step more and think about what is all the data in all of these cores, how it work with this. Some people say that HPC is also very much contributing to big data. We had big data long before the term big data came in the press. So this was always big data for us in HPC, large astrophysics simulation, large numerical weather prediction in ECWMF to predict the weather every day we have in our apps. This was always big data already in the past and continue to be so, because we strive towards exascale, so basically having lots of computing. But what we do with all of this computing is, of course, now the big question. We have to load data and basically put out data, right? The results of a parallel execution. And to handle this is, of course, also not that easy, because now we have a very large system, as you have seen in the architecture, with different topologies. So how, as an application scientist now, would basically work with this? And there is a course that you already, maybe some of you know. There will be a complementary cloud computing and big data course, which tackles the idea of data sciences a little bit differently and how clouds are doing it and with different technologies than here in the HPC course. So here we attract our, let's say, focus primarily really on HPC systems. There are different ways how to tackle big data, large quantities of data called cloud computing and so on. I will do that in another course, right, which is this fall. Just that you know that there's, of course, some other approaches here and there. And before we start with the data, I/O is something, I guess, who does know I/O? I hope everybody says I/O, input output of a computer. That's clear, right? So the I/O term is very dominant. You have sometimes I/O in terms of output on the screen, sometimes I/O in terms of output in a file. That's here and there difference, but it remains I/O. And it doesn't matter really where you are. If you have distributed memory, you have something in memory you want to basically put to file, to data, to disks in the past, or you basically have maybe shared memory. Also here you want to do things basically and put them on the file. So it doesn't matter which application you have. In other words, you really need basically to consider data in terms of really do parallel programming effectively. And because we want to do this within a MPI application, we want to do it in a very simple way, right? And this means I probably don't want to, have lots of management around this. So this should be given like the computing also by our infrastructure. Hence, you see a little bit this arrow indicating that when you have a large couple of racks, which usually stand for lots of computing, there are a couple of racks that you see here, for instance, which are storage facilities, storage elements, which are really closely connected to these clusters as well. And we will come to the point that, of course, everybody has a little bit local storage. We talk about that. But of course, the big global storage where you keep data longer or have data available is something which we have in specific systems. Also, there will be a sort of file system needed that is handling all of this. And we will talk about this as well. Going into the main of parallel file system, while in the other course, I talk a little bit about distributed file system techniques. For instance, Hadoop. I don't know if some people know Hadoop, Apache Hadoop or so, Hadoop distributed file system. You maybe have heard with Apache Spark using it and so on. So this is something we do in the other course. Here we have parallel file systems, which are enabling us to have a concurrent access to files. Cleaning is already ongoing, okay. Challenges. Okay, so what is there? The key problem you can see that firstly, we want to maybe sometimes have storage very long term. So we talk about tape archives. If you put petabytes into tapes, it takes a long time to get that on active disks again. So if you're a large big data application, you cannot just operate that on tapes. To get data out of tape archives, which takes the majority of storage and is very cheap compared to disks, takes a lot of time to go to this step, right? So you have something we call hierarchical storage management, where the long-term storage that you never use so quickly is put in tapes. And when you compute, you have more active disks, right, where you work with. This is another element to consider. Then for each, the number of files you read or write as a process. This is something what your application, of course, now has to program to see how you want to access it. And in order to do that at the time where your cluster has access, right, where you basically are scheduled, you have to have the data available. So if you have, let's say, scheduled the process now, and it's all in basically trapped in the tape, you cannot work with the data because alone getting it from the tape down to disks maybe takes a day or two, right? If you have many small kind of files. Hence, this data needs to be more beforehand available. You have to think about large data sets much more in advance. Today, we even do research where this is part of the schedule. So before your schedule comes, automatically gets data transferred, but it's still a little bit of a research thing. And if you can imagine that usually the problem is that every application domain is very different, how they store data, how they work with data, how they have metadata. So this is all elements which are to be considered here. And the parallel file system concept is now something where we can support something with specific types of file system with concurrent access to files. That's also something which most of you don't really realize. When you have a text file and you write something in and you open this text file again, you usually get a message in your laptop and say, wait, lost update, not good, right? Not having 2 times the same file open and then add here and add there. Or Excel table, right? You open it, one field is filled, you want to fill the other one. You better do this in the same process, not open it again, because then this will be a lost update and, race conditions around it. Hence, here we solve that with this physical idea of a parallel file system. There's even more topics around this, again, because it's related to it. I just do a pointer again. In the cloud computing course, we talk about different RAID levels. And there's this idea, if you heard from RAID, redundant array of inexpensive disks. It's something for data protection, to really have the data stored in a way that if you lose some data, you can restore it. It's something which data centers also have quite a lot of work with, and we also use it in HPC. In order to keep the course here and focus on MPI, I skip that and say that will be part of the cloud with different RAID levels for data protection, security, loss of data. Here we focus now how we can access this with MPI and how we now get this, let's say, physical data that we have into a logical perspective. Just shortly, examples of this parallel file systems that exist. So this is something you really have to buy as a HPC center, can be quite expensive. In EVM systems, there was always this general parallel file system, GPFS, very, let's say, renowned, a very good file system I worked 15 years or so with, quite good. At some point in time, around 2000 something, it was actually transferred. Maybe 10 years ago or so, it was actually going to something they call EBM spectrum scale, because big data came and they realized not only HPC can benefit from this parallel file system, also many other applications. Hence, they put that more in a marketing center, that it's a system for big data rather than just a parallel file system for HPC. Still, it has the same idea, concurrent access to file. And we will learn a little bit how that looks like and how that is supported in a minute. There's also Lustre, which is by far the most used these days. Lustre file systems are around. There are different open, let's say, consortia working on it, extending it. So it's, I think, the way of choice today. And in the past, there has been different researches going on different file systems. One is the PVFS, which also got some exposure. But today, there's even elements on Dropbox on this, or basically kind of cloud-like sharing systems on file systems. But this would be other examples. These are just one of the most common ones you have to understand. And what these are achieving is, so to speak, having a sort of two-level mapping. You have, of course, real I/O nodes and real storage nodes, but you basically don't really work with this. You have a file there, which is in a logical space, right? Hence is concurrent access to files. Because in the end, this logical file that you work with is not really existing and needs to be really in the physical nodes somewhere stored. In the end, we are limited. We still have our physical storage. We cannot have magic and suddenly say, well, we have an infinite storage, right? But this logical file now enables us, and with this parallel file system support, that we as application scientists, we don't care which node it is, where it is. I just work with one logical file. And the file system then just stores it somewhere on the disks, and we are fine with it. It also enables us that many different threads, or basically tasks, can access this file at the same time. And basically the I/O nodes and the whole logic of the parallel file system will enable us that there are no lost updates, that you have a very specific way how to access it. That this will be the couple of next slides when I show you how MPI specifically supports this. And of course, the parallel file system needs to support it on the lower level to enable then this logical file over different physical disks. Because in the end, there's of course a real disk somewhere where things are stored, right? So hence think about this two-level mapping, which leads me to a computer science technique, which is broader, just for your information. It's called striping. That's also in many different areas in computer science a part, where you can also then steer the striping factor and the unit of how much you want to have this logical file now put on different parts of the disks, right? But obviously that enables us a lot of possibilities, performance, throughput, how many writes and reads I can do. And this is something which is also often used in practice to configure this very system specific, how your system is really looking like, how many disks, racks you have, and so on. Just a side remark, because this is a more general computer science term, the striping. Now, how we realize this parallel file access. So normally you would have this inode, which essentially is a central part in Linux, for instance, for a file system block where you see all what's written in different directories and so on. So you can basically see it very similar. These concepts, of course, in a way remain. but the file name will be more in a kind of blockwise fashion, chunked away, and you should not really operate on it yourself, right? You have the MPI environment now that takes care of this for you. While normally you would do, different files, you would work with it. Here you would use the access via the MPI to store and, basically also read and write. Why? Because mostly it's also binary file formats. You cannot look into it and edit or do something. It doesn't make sense. It's specifically optimized for the machine, right, to do this. Hence, you need always a sort of library to access it. On top of MPI.io, you maybe have even HDF5, as I said, or NetCDF is also used basically in the earth sciences a lot. Parallel file formats. And with this, you basically have then the question of sequential consistency. So who is the first, right? And this is something which is then helping in these systems. Sequential consistency is a term again, also quite known in computer science. This is exactly what I told you with the laptop, right? So when you have essentially 2 times the same file open, now the race condition is who was first to write or who is last, then have a lost update. This is element which still needs to be there, and we can of course now think about different ways how to relax this sequential consistency. But of course, this would be also bad, right? You see, possible solutions would be you can lock the entire file, as we discussed in the laptop, or you basically have some semantics where you say, you as application developer are responsible. You have a file pointer in the file, and you have to do it, and you basically are responsible. Or you lock different file partitions or certain elements of the file. Let's say the first megabyte is this, the second megabyte is that. There would be different ways how you can basically work with this. Hence, this is the locking entire file, certainly from the laptop area, but we work with some other semantics basically inside the parallel applications, which brings me now to this file pointers, right? You have a huge file, as we said, a huge logical file, where you now have shared file pointers, where you can now in different areas of the file seek a certain location and write for a certain length, for instance. And this is allowed by the parallel file system. So you don't get a message, well, warning, the 500 other cores are already using that file. All can access the file. And of course, you have then also, as a developer, really to ensure that you do this in a really good way. Now, the good news is when you do that now, really like here, go into this file, would do this manually, you can imagine many errors will probably follow. Hence, MPI supports us a little bit again with the environment to write and read with MPI commands instead of doing it just by hand. Hence, it brings us to the MPI-O. Of course, here again, for the performance and for the overview of the MPI application perspective, it is also a source of load imbalance. It's also a source of parallel performance issues. We need I/O. For instance, as I said, rank 0 reads in all the topography. Let's assume the topography is a couple of gigabytes of a whole world for, let's say, climate simulation. This could mean that rank 0 is very busy for an hour and all the other cores don't do anything. Hence, quite bad, right? To have a rank 0, one master worker scheme to apply here. So what could be now possibilities of supporting what we said before with this I/O to make it scalable and to enable now the shared location to a file so that we maybe can all read the topography and regional elements at the same time and write our, let's say, results at the same time. And this is exactly where MPI.io basically comes for. Needless to say, what I said before at the end of the other lecture, we still have performance impacts. It looks beautiful, MPI.io. You will see the commands are quite nice. The logic behind this is nice. We're still limited by the throughput, of course, of the tree, for instance, right? That we oversubscribed. We basically limit by the mesh character, by the network interconnectivity. We don't see that as application developer. We just do MPI. But underneath, of course, is a real physical system, which would have bottlenecks. And this could be also something which can be hard to detect because essentially you abstract so much away nicely from MPI.io that you don't anymore think about the dedicated I/O nodes. The kind of load has to travel a couple of nodes to really then get written to a file and so on. So what are ways how to do it with I/O? They are all basically collective operations. some certain, let's say, rank that just want to drop some configuration parameters, which are maybe for the whole application. Oops, that's not so good, especially when we record. Your internet connection is unstable. See a bit. It looks good still. Okay. Hence, take that into account when we talk about this. It's nice abstraction. And we now look at different ways how you, of course, do this, and we'll also understand these limitations and these possibilities. Hence, the first one I already talked to you is, you could have this so-called serial I/O, the master worker. I collect everything from everyone, and then I have the certain role as a specific rank and drop everything to one file to disk. So immediately you would think, when I have a very, very huge application with lots of processes, this will not work or will cause significant load imbalance. Hence, this is something what you rather not do. It's slow. It's very some things which is maybe for smaller MPI applications or for very specific small elements in the application for configuration parameters, where this sending and receiving is very quick, and then you drop it to file, but usually would not go that way. In the other end of the scale, you would say, when we say it's anyway regional, why not everybody keeps one file on its own, right? And then does this I/O read on. In a way, now every process is responsible, could read the regional parts of the topography of the world in, but then you have certain file system limitations usually. What it literally means that on the disk, you have now millions of files eventually when you have lots of tasks. Right? Hence, I call that the inode challenge, for instance. You will see that on our HPC clusters, they're not supporting that anymore. They're breaking by so many files to handle, to manage, because every file needs an entry, of course, in the different inodes and so on. Hence, this is also not really working at scale. And this, what would be now the real idea, you have this sort of shared file I was talking to. But instead of managing now the process that everyone has one file, we do this so-called shared file. Hence, we have a shared file pointer from everyone addressing and can write in this, let's say, logical file, as I was explaining earlier. And then it will be dropped to disk as one file, striped over real different nodes, right? But me as application developer, which is this perspective now, I don't care about this. I just can have, all of these different ones do all their I/O in a shared file, and with this get really parallel performance. Of course, think about then the underlying network means you have to travel a lot through coming to the I/O nodes, as I was explaining in one of the slides. Of course, you have performance impacts. So let's look a little bit how that would look like. So you would have a file, and also there will be some demonstrations. So if you don't get everything, we will see how that materializes in the practical lectures, right? We have a file name, a logical file name that we would have. We have our MPI elements that we anyway have, MPI finalize and so on, our rank. And then I can basically create a certain file and a file handle, as we call that, right? Because with this file handle, I can now do certain things, which is the file handle and the info here. And you see here one element of ordered, where you have then basically the writing process ordered by the ranks. So your output would look beautiful. And also here you have an MPI file, right, where the first come, first served, so to speak, will be writing it. Now, for this to really work nicely, you need, of course, the parallel file system underneath, especially if you want to have a very big data element. But what you see is quite good abstraction from the lower level, right? You don't know anything about where it's stored, what it's stored, maybe maximum the file name. And then that's it. You can say create it. You can say in which, of course, communicator world it will live. It's important. It's always important for us. Read and write. You can protect it a little bit. So that is good for programming if you want maybe just a topography to read and not to change. These are elements that you basically have to do. The same is actually true for read. There's another command called read that you can use. And then you close the file handle, and it's all binary. We will see that also in the demo. Hence, you have a nice abstraction of something which is then nice supported by the environment. That doesn't stop there. The application developers even go to this element of saying, we have the specific libraries now. And we have this I/O hardware, the real disks. We have the parallel file system, GPFS, Lustre, managing the concurrent access to file, all of them. We have the environment of MPI I/O, saying we have all the MPI functions that I do, but they're still on the way of having, something to write to a file or something to read for a file. Hence, they are so-called high-level I/O libraries, like netcdf or HDF5, for instance, in the moment, hierarchical data format, which have a certain way how you store files in a community, for instance. So you have a certain standard hierarchical data format. You can see essentially almost like a file system in a file, right? So you have a structured hierarchy, and you can define as a community how you really store the data. And you will just be really working on this particular HDF level. So you would assume that this topography information is always in /topography. So there would be the rainfall or the precipitation levels would be in /precipitation. So there will be a structured way how you do it. And even these libraries take advantage of MPI-I/O. So in other words, you work more and more on an abstract scientist level instead of really the low-level disk level, right? Because this would distract you. It would take you lots of management, to take you lots of, let's say, striping of different disks. And so you don't want to do any of this. You just want to focus on your application. And even there, it's nicely supported with high-level I/O libraries. As I said, HDF5 is just one example. There's also netcdf. They actually, at some point in time, are always discussions to merge them. The trouble is that pnetcdf, parallel netcdf, and so on, they have certain different old versions, and many different applications not always support the cutting edge standard now, but also older standards. You have seen that in the video. We have some other applications which needs to be backwards compatible. Hence, it's not so easy to just move always to the best standards that we have today. And in a way, that's really how the application people then work with it, right? So they don't really think much about the I/O hardware. Of course, when you do an application, for instance, in your HPC to one of these systems I was alluding to, Leonardo, Lumi, you also have to specify how much petabytes you want to store, how much gigabytes you want to store, right? And then you would quickly get questions and so on. When I say petabytes, is this really an active, kind of need in the application, or is it just the output file? Hence, there would be different levels how we have to specify. And we will go in one of the lectures through one application process so that you know a little bit also how that works when you want to apply yourself for computing time. You have to do different levels. One is the output, which maybe stays there for other researchers to reinvestigate, to write papers to. The other one is also what you really need in the computing. So hence, these are not the same things, right? They're different levels again, how to do this, but you access those still with these different libraries you see here. Hence, you have this binary file where you rarely do a more and look into the file. You rather would use always these libraries to print out and to see something. One example, for instance, in this is the HPDB scan. It's an application of clustering where we load in, obviously, lots of different points, right? It is a point clouds of Bremen, for instance, that we once used to actually get these plots. So we load that in using parallel I/O. And then what happens is this clustering is done by computing, doing the clustering rules, and we write it again to file. And in this HDF5, we have just basically a /clusters and would basically for each point assign your cluster 1, your cluster 2, your cluster 3, your cluster 4. That's basically how it works. But it is all binary. You cannot look into it. And that's how it is basically a kind of, a real practical example that, we will demonstrate also in 4.1 much more about this, so where it becomes more clearer in this. Hence, it's really used, this MPI I/O, and also the on-top libraries. We use HDF5, as I said, especially here for, but also in many other applications. That is something which is needed. Hence, don't forget the view of I/O. Here's a quite interesting video as well. I could talk there much more longer about it, different file formats, what you can use in MPI. You can have advanced file formats where you create your own different types, combined maybe of an integer, a char, bound that together. So these will be all topics of advanced data with MPI. And I think for now, that's enough. I think your head is already bursting because, you know, we had computing, non-blocking communication, networking underneath. Now the data perspective. I admittedly think it's quite an advanced MPI teaching lecture today, but that was also the title. And now that is also our last conceptual one about MPI. We will proceed with OpenMP, but in between we will have some interesting practical lectures. Also remember, we try with Rescale to also have an interesting lecture for you. And the next one will be really on practical subjects here. So if you don't really understood everything, I think the practical ones will also help you a little bit understanding what we learned today. Remember also the one on Monday will be, of course, pre-recorded. So see you probably next Tuesday.